Okay, maybe I'll just start then. So first, let me say on behalf of both myself and Arun, thanks very much for the invitation to give a talk in this seminar series. What I'm going to cover today is basically the first part of what we did in this recent paper, as Irina already mentioned, and then I'll hand it over to Arun. Let's see if this works. So I'll do the first part, and it's going to be basically from a physics point of view, a physicist point of view on why we might be interested in computing things related to Bordism groups in the context of the Swampland conjecture and Swampland program. And then we're actually going to kind of go under the hood and look at how some of the computations were done. And that's when I'll hand it off to Arun. Okay, so what I'm going to cover is based on basically this top paper, this 2302 paper with Arun Debré, Marcus Dirigil, and Miguel Montero. There's some related work studying some of the physical properties of some of the objects we found, which actually appeared slightly earlier. Of course, they're kind of closely linked together with the same with Marcus, Miguel, but also with my student Ethan Torres, who's graduating and moving on to CERN fairly soon. And then there's some other work, some earlier work, where we explored kind of some other aspects of Bordism groups and their relations to aspects of duality symmetries, both in type 2b and in F theory. Okay, and I might as well mention, I mean, there's too many papers now to list, but there's various permutations and combinations of a number of people, authors I've listed here. Sorry if I forgot your name, working on things related to, you might say, Bordism group calculations and their relevance for things connected with the Swampland program. So, the ... is to indicate that I probably missed some folks, and there's probably stuff in progress that we'll hopefully, we'll see in the coming years or coming months and years. Okay, so here's a picture of Tubordia as put together by Marcus's friend, Paco Giudice, and it has various elements to it. I'm not sure it can be completely seen, but we have a nice image in the paper you can kind of zoom in on it if you like. And there's basically different types of paths one might take through the calculations we're going to do. And what I'm going to do is focus basically on this path associated with building up some of the physics intuition about why we might be interested in certain calculations. And Arun will basically be covering more aspects of how some of those calculations were actually done from a mathematical perspective. So what's the general motivation, or why might we be interested in these kinds of questions? So broadly speaking, even beyond, say, Swampland, or just, in the context of high energy theory, or even more broadly in the context of quantum fields and strings, one reason to be interested in this is because it provides kind of a new handle on looking at questions connected with non-perturbative phenomena. So as is famously known, many non-perturbative features of strings and quantum field theories really became heavily, we could actually understand them in a much greater detail than was possible in the past due to structures such as supersymmetry. And that's still true today, and it continues on. However, at the same time, it's worth pointing out that, we haven't seen any superpartners yet, and there's a big question about what is actually the scale of supersymmetry breaking. Is it down at the TeV scale? Is it all the way up at the Planck scale, or somewhere in between? Not so clear. I'm on the more optimistic side, although I think many of my colleagues are more pessimistic these days. But in view of that, it's also natural to ask for whether there are other tools that might be helpful, complementary to things we already know, which might help to provide additional information on non-perturbative phenomena in strings and quantum field theory. And at least in the last 10 years, this has really become a very powerful method for looking at many, many different features of both quantum field theory, string theory, condensed matter physics. It has many applications, and that's going to be kind of the underlying theme, not just here in the Swampland context, but more broadly as well. Of course, I'm going to be applying it in the context of Swampland conjecture, but the idea is that topological structures can actually provide important insights into non-perturbative phenomena. Okay, so what's this talk going to be about? On the one hand, I'm going to be talking about the cobordism conjecture, so I'll briefly review what that is, although I have a feeling that for this audience, I don't have to probably spend as much time on it. And on the other hand, I'll be talking about the spectrum of type 2b strings, or its non-perturbative lift, to F theory. And what we're going to be doing is kind of twofold. One thing we're going to be doing is asking whether the cobordism conjecture, it is a conjecture after all, whether we can test it at all. And what we're going to do is use things we know about supersymmetric backgrounds primarily to test whether we can see that the cobordism conjecture correctly produces the expected objects that we expect from supersymmetric considerations. But then once we have those tests in place, what I'm then going to do is assume that the conjecture is true and then ask, okay, does this allow us to predict or get a handle on possibly new kinds of objects that may be difficult to access using purely supersymmetric techniques? So those will be the kind of the twofold applications of what we'll be doing in this talk. Okay, so at some level, testing is going to involve rediscovering supersymmetric backgrounds you might have known about from other methods, but perhaps even there we can shed new light on the kinds of things that cobordism conjecture is telling us about such backgrounds. And on the other hand, we're going to be trying to access non-supersymmetric objects. Okay, so I've already said that. So let me now begin by briefly reviewing swampland cobordism conjecture. And as I mentioned, so this was something put forward by McNamara and Vafa in 2019. And okay, here it is. Here's the conjecture. The Bordism group of quantum gravity is trivial. Okay, so as I've written it here, this is kind of a meaningless statement because I haven't told you what a Bordism group is. And strictly speaking, even to a mathematician, defining what you mean by the Bordism group of quantum gravity is quite vague. There is no mathematical definition of this thing, but in practice, it actually becomes rather sharp, as we're going to see in just a minute. Now, from a physical point of view, you can say that there's kind of two operating things that motivate this kind of conjecture. One is no global symmetries in quantum gravity, and this is kind of one of the underlying motivations for this. And a related point is that, in fact, as we're going to see, completeness of the spectrum is in some sense intimately tied to the condition that the Bordism group of quantum gravity is supposed to be trivial. So I'll explain both of these points as we go. Okay, so what's a cobordism? So the general idea is we're going to specify over here on the left or here on the right some choice of a k-dimensional manifold. I mean, what might equip it with additional structures. So for example, if we're doing gauge theory, you might have a particular kind of bundle we want to put on it. Might be a line bundle or a vector bundle, something like that. Or we might have specific conditions on, say, fermions transforming as spinors, or it may be some more general spin C or some other twisted spin structure. And we want to retain all that structure. And what we want to know, the game we're going to play at the level of cobordisms is if I give you, say, a k-dimensional manifold equipped with all these bundles on the left and another one on the right, can I find you kind of a bulk k+1 dimensional interpolating space, which has as boundaries these things on the left and right. So that's our kind of equivalence relation. So what we're going to be doing is looking not so much for specific manifolds, but rather equivalence classes. So can we say that we would say in this case that this bundle over here, or this manifold here equipped with this bundle is equivalent. It's in the same equivalence class as the one over here on the right. Now, why might you be interested in this in the context of quantum gravity? Well, there's kind of a general intuition that, you know, the path integral allows us to interpolate and do non-trivial transitions. There are celebrated examples of this in string theory. We have different kinds of topological transitions. Betty numbers can jump around. A natural question is, okay, how loose is this proposition? And how general is it? So does anything go? Does anything connect to anything else? Or are there more general kind of constraints you might want to impose? So for example, if you're a quantum field theorist, you might say, well, I think I know what I mean by a different, a specific space-time and a gauge bundle that I want to talk about. Do I really need, what's the sense in which gravity is going to allow me to connect to anybody else? We're going to be addressing this at the level, not so much at the full level of quantum gravity, but more at the level of, say, effective actions and the path integral that we get from, say, the gravitational path integral and supergravity. So kind of long distance limits associated with quantum gravity. And even there, we're going to see that there's something non-trivial that can emerge. Okay, so just to kind of fill out the story slightly more. Sorry, is there a question? Or... Okay. So just to fill out the story a little bit more, in the context of a cobordism group, this object, omega kg, it's a collection of manifolds, and it turns out that they actually form an abelian group. So you can add them together. So here's my addition operation, and they make some sum over here. There's a notion of an identity element. So if I add this on at any point, it doesn't really change the interpolating bulk manifold. And one can also speak of inverses. In the case where you have something like the integers, then it's usually something like orientation reversal. And in cases where it's not oriented Bordism, you can still speak of usually some kind of finite order group, and so it will naturally have some kind of inverse associated to it. Okay, so just so we're all on the same page, I'll give you a quick example of how a Bordism, two things can be Bordant, even though you might say non-trivial that they shouldn't be. So let's consider a two torus, or kind of the surface of this donut here, and also a two sphere, so a genus 1 and a genus 0 Riemann surface. So it turns out that these two are Bordant to one another. How could this possibly be? I thought genus was a good topological invariant. Well, it turns out that I can take the solid donut, so the one that has as boundary this two torus, and scoop out a little ball, so a donut hole getting scooped out from the interior of the donut. So the boundary of that thing is a two sphere for the donut hole, but on the other hand, the boundary of the donut is indeed just a T2. So this provides us an example of a Bordism. What's going on if you tried to run a movie interpolating from the T2 to the S2 would be that it would look like the T2 is kind of pinching off and becoming extremely degenerate. So in this sense, Bordism is a rather coarse way of making an equivalence class between different kinds of manifolds. Nevertheless, we're going to see that it's still not, it's coarse, but it's not so coarse that we lose all information. So here's what the groups typically look like. They usually look like a finite product of a bunch of integers and then some torsional factors. So these are z mod some prime p raised to some power. So these are what we call torsion, and these are what we call the free factors. So just to keep going a little bit more, let's go back to the cobordism conjecture. How is this relevant in the context of quantum gravity and the swampline conjecture? So the idea is we have this, we can consider, for example, a d-dimensional gravitational theory. And I'm free to kind of split it. Let's imagine we're on flat space asymptotically. We're going to split it into two factors of kind of products of the reals. So I'll put k plus 1 over here and d minus k plus 1 over here. Okay, now let's imagine that we want to try and add a defect. So this will be codimension k plus 1. So we're imagining that it fills all of the directions indicated by the purple over here. And then it just sits as some point, which I've kind of fattened up a little bit over here inside of a transverse k plus 1 dimensional space. So I've added a defect, and we have many examples of these in the context of string theory or other systems. For example, D-branes are a good example that fill some regions of space-time and then sit as sit as points in other transverse directions. But now what we're going to do is we're going to say, okay, I can build you now an interesting class of objects by considering my k-dimensional manifold and then attaching a little tube along it. And I might view this as a cobordism defect. So what's going on? From the perspective of somebody who lives very far away from where this tube-like region was stuck into the geometry, it's going to look like we have some kind of defect, like this. And in fact, one can argue, as McNamara and Vafa did, that this is giving you an extended object, and it's actually charged under a so-called p-form symmetry. The symmetry group in question turns out to be the Pontryagin dual of that Bordism group I was telling you here. It's just basically maps from the Bordism group into U1. And by basically studying different kinds of black objects that one could consider, one can argue that, in fact, it's actually a global symmetry. There's no like direct string attached between this and kind of going out. So the black hole doesn't really know about picking up a charge under this thing, under this group. Okay, but I thought we said that in quantum gravity, there were no global symmetries. So something either has to come along and gauge this thing or break it explicitly.
I think you mean RK, right?
No.
Is the object charged under the symmetry?
I mean MK here because this is the bulk k plus 1 dimensional manifold.
So this is a cobordism defect or a gravitational soliton charged under cobordism?
This is a cobordism defect, I think.
Okay, then sure.
Yeah. Okay, thanks. Okay, so the upshot of all this, or where the juice really comes into it, is that if you now say, oh, but I expect this thing to be trivial, well, we just computed this thing is non-trivial. So we're predicting, or this is the expectation from the cobordism conjecture, is that you get a new object. So anytime you calculate a cobordism group and you have your favorite symmetry that you think is present, if you ever get it to be non-zero, you are predicting the existence of some kind of new object. And I've indicated what one such thing might be. And I've tried to indicate there's like some kind of little flux lines emanating out. So here's two pictures of that little defect, one from kind of a bird's eye view and one from more the side view that we already looked at over here. So you should think about this as kind of the k-dimensional boundary over here, and then stuck at kind of the interior, the thing that's kind of sourcing off some flux is this like point-like thing in the middle. Okay, so right. So basically, in other words, if we ever calculate a non-zero value for this Bordism group, we're predicting, or the conjecture of McNamara and Vafa is predicting a corresponding codimension k+1 defect in our system. So what we're going to do is now try and test it in the specific context of 2B and F theory. So I'm going to focus on the 2B duality group. What's the 2B duality group? Well, if you look at a textbook, you'll get one answer, which is not necessarily correct. So at the most basic level, so folks knew from supergravity that there's a celebrated SL2R duality group. And as is usually stated in textbooks and various reviews, this is broken to say SL2Z. Now, this is not quite correct, and you know it's not quite correct because you need to specify how the fermions will act or get acted on by dualities. And this leads you to what's known as a spin cover of SL2. And in a specific case where it's SL2 and not like SL3 or whatever, this is what's called the metaplectic cover of MP2Z. But even that's not enough. If you allow yourself so-called reflections on the F theory torus, or by M theory, F theory duality, noting that M theory has a PIM plus structure, you actually have to consider the PIM plus cover of GL2Z. So GL versus SL, you're allowing yourself things that reflect the so-called F theory torus. I'll explain that in just a moment. So this actually turns out to be the full duality group. Okay, so here's the reflections from the perspective of an F theory model. So the idea, remember, in F theory is that the axiodilaton becomes some torus like this, and we can consider reflections either this way or that way. Okay, so these are elements of GL2Z rather than SL2 because their determinant is -1. In terms of 2B worldsheet actions, one looks like orientation reversal, omega, and this one here is what we call left moving fermion parity. So in other words, it just takes the left movers and flips their signs. Okay, now if you're doing type 2B or it's a lift to F theory, you can think about F theory as basically just some very clever way of solving the Einstein field equations in the presence of sources, so axiodilatons with non-trivial profile. And so as we kind of move around in that geometry, things can become singular, and usually these singularities indicate the presence of a 7-brane. So 7-brane in particular is a particular kind of real codimension 2 defect from this point of view. Okay, so what's the structure group that we're going to talk about in the context of our Bordism group calculations? There's this script G, which is going to be involving the spin structure of the spacetime, or really this MK, this bounding manifold, and we're going to fold that in with the duality group. But I quotiented here by a Z2 diagonal, and this is because when we look at, say, F theory or things like that, the way that we're actually solving things is mixing things we do in terms of the tangential structure, for example, and things we do in terms of the duality. So these duality actions actually get intimately mixed up with things you've done in the spacetime. That's the kind of nice feature of something like F theory, and it automatically encodes that geometrically. So this is going to be the symmetry group, if you like, that we're going to be interested in. It involves both the tangential structure and also a choice of duality bundle. Okay, so what's going to be why are we doing this? Well, the Z2 factor is kind of a common diagonal from this one and that one, the spin K and the G duality. So just to remind you, spin K can be thought of as a double cover over SOK. And similarly, the duality bundles that we talked about, if we include the contribution from fermions. So similarly to how, if we want to talk about rotations of vectors versus spinners, we have to include spinners. It's similar here with this MP and GL plus. These are the analogous things. This is the analogous spin lift of SL2, and GL plus is the analogous pin lift of pin plus lift of GL. So the Z2 here, diagonal, is the diagonal subgroup of this one here, and that one there. That's the one we're quotienting by. So here's what we computed. These omega kgs were the different choices of these. So here's the big table. Can't see it because of the zoom control. Hopefully you can see it. So this is, if you like, the warm-up example. And then there's a bunch of supersymmetric objects we looked at, and then supersymmetric plus non-supersymmetric. So the spin MP, those are the ones where we just take the minimal SL2 and then just ask that we extend it to include fermions. That's what we get from the spin MP. And if we look at spin GL plus, that's including both actions on fermions, but also allowing ourselves reflections. And those reflections typically lead to non-supersymmetric structures. And so in this sense, these will be where we test the Bordism conjecture, cobordism conjecture, and this will be where we actually put it to use to try and see if we can get new kinds of objects. And this, as I mentioned, is a warm-up, but it's a very useful warm-up because basically, once you calculate this, then there's additional stuff you feed in to get the rest of the Bordism group calculations. Okay, so you'll notice that the K here is running from 0 all the way up to 9. So remember, we're talking about a codimension K plus 1 defect. So 9 is the max we can go if it's a 10-dimensional spacetime. K equals 10 is useful for talking about certain discrete parameters like discrete theta angles in these theories. These are what they are, the Bordism groups for those. And if you go all the way up to K equals 11, then you're actually studying duality anomalies. And interestingly, as we found in a previous work that I cited at the beginning, one can actually show that the 2B action that one writes down in textbooks actually has a very subtle duality anomaly, which you can cure by adding a very subtle topological term. But this is how you would study it, by first writing down the equivalence classes of manifolds and then studying appropriate anomaly topological field theories. Okay, I'm basically going to focus on kind of the top rows as will Arun, but I just want to kind of give an overview of this. Okay, so let's interpret these things. I already said this, but I'll say it again. For the spin MP, we're talking about supersymmetric defect. And for spin GL+, we're talking about both supersymmetric and non-supersymmetric stuff. Okay, so let me just briefly go through these. These are the ones where we're expecting to recover known backgrounds. Okay, so here they are. I'm going to focus on K odd because those are where we actually find the most interesting things. K even is, roughly speaking, already covered by things discussed in McNamara-Vafa. So one recovers by doing this various kinds of backgrounds. These L's here are lens spaces equipped with a specific duality bundle. The sub 4 means it's a mod Z4, and the 1 just means it's a circle. The 3 here means it's a 3-sphere. 5 means it's a 5-sphere, and so on. And they get a little more complicated. I'm not going to go through every single one. But the point is that we were able to recognize that these things were the boundary geometries associated with specific defects we already knew about in many cases in string construction. So for example, the celebrated PQ7 branes of F theory show up naturally. Non-Higgsable clusters, which show up in the classification of 6-dimensional F theory vacua, as well as in 6-dimensional CFT, show up. S-folds, which appear in n=3 theories, 4D n=3 theories, also make an important appearance, as do many other things. I should mention that some of these lower dimensional ones, we weren't aware of finding these. We weren't able to find these things directly in the literature, but they kind of naturally follow if you follow your nose from things you know about the higher dimensional cases. Okay, so typically these things look like boundaries of this kind. It's like a bunch of copies of the complex numbers, the F theory torus, and then you quotient by a finite group. And the boundary for Cn is just some sphere of some dimension. And so this is the sense in which we're getting generalized lens spaces. And then the T2, because it's twisted in with this group action, gives you some more general type of duality bundle over a lens space. And so using what we know about supersymmetric backgrounds, we can often kind of make a good educated guess about what the generator for the Bordism group is going to be. So here are some examples for K=1, a 7-brane of a specific type and another 7-brane of another specific type. So the E6 here refers to the gauge group that the 7-brane carries. So the exceptional group of rank 6 and the exceptional group of rank 7. So here they are again. There's specific values of the axiodilaton that are actually preferred by these choices of 7 branes. And the Z3 generator of the board, the spin MP, is over here, and the Z8 generator is over here. So this is what you can actually go. And you can go through this for basically all the other ones as well. Now, just to kind of expand on this slightly more, because it will be useful for Arun's part of the talk, there's something very special about tau equals e to the 2 pi I over 3, or SL2 equivalent to e to the 2 pi over 6, and tau equals I. These particular values turn out to be fixed by subgroups of a finite subgroup of SL2Z. And you might ask, okay, that's very interesting. Is there a sense in which everything could be built out of those kinds of subgroups? And indeed, mathematically speaking, there is. So it turns out that there's a very interesting structure called an amalgamated product. You can think about this as basically a free product, so don't impose any relations, but then impose kind of a Z2 identification across, say, a Z6 and a Z4. And you could do it again for MP2. The Z6 right here is associated with that Z3 right there, which is in turn associated with that E6 right there. Oops. And the E7 is associated with the other guy, the Z4, and its spin lift to Z8. And in fact, you can go even further and talk about GL plus. These things down here are more, well, they're nastier groups, you might say. They're the dihedral groups associated with symmetries of associated n-gon. The sub 24 means it's an order 24 group. That's our notation. And then there's a, order 8 identification going on here. So the D8, for example, to reference yourself, is associated with symmetries of a square, a Z2 semi-direct on a Z4. So in other words, the building blocks that we're going to actually physically speaking use are all associated with these 7 lines. Okay, so that's all I'm going to say about spin MP. You can say a lot more and go through a very long set of checks. But let me now move on to the GL plus generators. And you find some of your old friends from the supersymmetric case, but you actually lose some of them and you gain new friends. So some of your friends turn out to be eaten or killed by your new friends. So in particular, there's this new object, this R7 ring, which I'll focus on. And you can also recognize that there's many other objects that get generated. One of the interesting things is that the lower Bordism groups are usually inherited straight from the things we already knew about in the supersymmetric context, as well as basically compactifications involving the reflection 7 brane. And one can also show that there's related things involving orientifold planes. That's not too shocking because we're including reflections. But kind of the main driver for the show is that basically the one new object which seems to be popping out is this reflection 7 brane and its subsequent compactifications down to more complicated spaces. Okay, so what is this new object? So this is the one I already mentioned was studied from a physics point of view over here and was kind of discovered from a Bordism point of view over here. The Bordism group is actually now Z2 cross Z2 if we look at codimension 2, real codimension 2 defects. So the E7 7 brane does this on the axial dilaton. So if you wind around it, it basically implements an S duality generator. So tau goes to -1 over tau. And if you do the R7 brane, you get something a little bit different. It's a non-holomorphic operation. So how do I know it's non-holomorphic? Well, pictorially, look, tau is going to minus tau bar. It's a non-holomorphic operation. So it's pretty clear it's not going to be supersymmetric. And you can check it in more detail. It's true it's not supersymmetric. And you might also ask, well, I thought I had like a Z3 generator in the case of MP. What happened to it? So our new friend is going to eat our old friend. So for example, we have this Bordism of the order 3 element. That's what we mean by it's null Borden. Using a reflection 7 brane, we can flip the G to a G inverse and then cap it off like so. Doing so, what we find is that the original Z3 generator turns out to be trivial in Bordism. So that's a non-trivial feature of this. So you both gain new things because you have a new group to play with, but at the same time, having a bigger group means that certain previously independent generators are now eaten up. Okay, so what I've told you about so far is basically the path followed by a physicist through this. And what Arun is now going to do is follow this other path. And of course, these paths, even though they look distinct, are closely related to one another. So I'm now going to hand it over to Arun, who's going to tell you more about the second part, doing these calculations in more detail. Okay, so I'll stop there. Should we pause for questions or should we just go straight to Arun? Maybe it's better to just go straight to Arun.
Yeah, I think Arun can start sharing the screen. If someone has a question, meanwhile, can ask, but otherwise I would let the general questions for the end.
Okay, so Arun, do you want to take it now?
I'm on it.
Okay, great.
Okay. It looks like people, okay, can people see my screen?
Yes,
yeah,
perfect.
looks good.
And yeah, just
Awesome.
a reminder, if anyone has a question, can just unmute yourself and ask. Okay.
Yeah. I will keep chat open, but probably better just to, if it's possible, to say something if you have questions for me. So first of all, thanks everyone for coming. Thanks to the organizers for inviting me and Jonathan. And thanks, Jonathan, for a great first half of the talk. So what I'm going to do for the second half is I'm going to talk about some of the, you saw this table that Jonathan showed of all these computations that we did. And I'm going to show you how sort of the beginning of the story. In half an hour, we can't walk through the whole computation, unfortunately, but I'll show you the techniques we use and the, really seeing them through for a couple examples, including the Bordism group, which gave rise to the R7 brane. So let's see. So I'm going to go ahead. So The way that I like to think about this is I'm coming from mathematics, where the algebraic topologists have been thinking about their own computational problems for decades and decades and decades. Like the first Bordism problems were really solved in the 50s. And so I like to think of it as like the topologists, they've been carefully sharpening their knives for a very long time. And now we have these problems for them to sink their knives into. And that is the way that these computations go, is that using these pre-existing tools that have been heavily developed and well understood, we get to solve problems that are easier than the ones that the topologists are solving. So that's, and it's really nice to be able to work in that area. So what we're gonna do is we're gonna focus on omega 1, the Bordism group of 1 manifolds. And because this corresponds to 7 branes under the McNamara-Vafa cobordism conjecture. And so we're going to consider these three duality groups that Jonathan mentioned. What we're going to get is very close to the abelianization. In 2 cases, it's literally the abelianization. And in the 3rd case, there's an extra Z2. So as Jonathan mentioned, here's the table. So we're going to focus on omega 1, which is this, but we computed all of these other groups. And the techniques are essentially the same as what I'm going to talk about today. Just, you have to push them a little farther. Before I go on, how much time do I have? Like, what time should I cut off for questions?
I mean, typically, we always say like 45 minutes plus questions to have a lot of questions. In the end, it's going to be 1 hour. We'll see how it goes. So just, I don't know, think about 20 minutes more, 25.
Great, I can do that. Thanks.
Maybe I can also ask, since we stopped, actually I had this question before as well, but yeah, when you have the distinction between SUSY and non-SUSY and so on, what is the information you need to say this? Like you compute the cobordism group and how you know if it's going to be non-SUSY or SUSY?
Well, you check whether the spinners are being preserved, the supercharges are being preserved at the boundary space.
It's not exactly a math question. Like, so we started off looking at spin GL plus because that was the correct duality group in full generality. And then it turned out, what did we get out at the end? Oh, look, these things don't preserve supersymmetry. This is my point of view on it, and it may not be the fully correct one. But it's
maybe I can make a comment. I think there is the math. You can view the math question as saying, given a cobordism class, is there a representative of that class that preserves some SUSY?
Right.
So technically that is a math question, but I think it's actually a very, very hard math question in general.
Yeah. Maybe a better way to say it is that for the representatives in the equivalence classes we found, we could then check whether they preserve supersymmetry, and the answer was no. So in that sense, it was non-SUSY. And it kind of morally makes sense because you're sending a holomorphic thing to a non-holomorphic thing.
But it's enough if you have just one representative, like one example, and you check it for that example, and that already tells you if all of them.
Well, so it's a little bit trickier than that because, for example, we had if you go down to the lower ones, we had, for example, compactifications of R7 branes, and there was another generator
and here.
Yeah, but there were generators that could also be interpreted as like orientifold planes. So at that level, you might say, well, an orientifold plane is perfectly good with supersymmetry. What's going on? But in most of the cases, there was no such option available. So so this is the sense which it's SUSY and non-SUSY, as we wrote. I hope that helps.
Yeah, that was a great question. Should I guess, are there more questions now?
I don't know. You
okay.
can get moving.
Okay, yeah, I'll go on. So this is the full table of stuff that we computed. I'm going to focus, as mentioned, on degree 1. So the 3 groups that appeared in the table, there's SL2Z, MP2Z, and GL plus 2Z. So all these 3 groups, Jonathan mentioned this, they are what are called amalgamated products. So this is a way of decomposing them into simpler pieces. And because this particular way of decomposing groups greatly simplifies the corresponding Bordism groups. So we saw SL2. This one is a relatively well-known amalgamation. SL2 is Z4 and Z6 amalgamated over Z2. MP2 is the spin double cover. So you just double everything, Z4 to Z8, Z6 to Z12, Z2 to Z4. GL2 plus, you throw in a reflection. And now Z8 enlarges to D16, if you add a reflection to Z8, you get a dihedral group, Z12 to Z24, Z4 to Z8. So remember, these are dihedral groups, not binary dihedral groups, which I understand are the more commonly appearing things with this notation in string theory. So this is really the rotations and reflections of an octagon, the rotations and reflections of a dodecagon, the rotations and reflections of a square. So the actual Bordism computation for SL2 is relatively straightforward. For MP2 and GL+2, we have to invoke something called the atom spectral sequence, but I'll tell you how that goes. And the story is pretty similar for the two of them. The details of the computation may differ, but the sort of outline and how things work is pretty similar. So another technique, which was crucial for us, is something that, again, we borrowed from the homotopy theorists who have been doing it for a long time, and it's the notion of working one prime at a time. So as Jonathan mentioned, the Bordism groups are finitely generated abelian groups. Let me try this. And so what that means is there's this decomposition where you say, okay, there's the free part and there's the torsion part. And the key point is you can isolate the free part and you can isolate the p torsion for each prime p using different techniques. So for example, the free part is easy. I don't know why it's doing that, I'm sorry. And the torsion parts are usually harder. They get harder as the prime gets smaller, in fact. But the point is, different methods address different pieces. And so, and each of them is simpler than working with the entirety of say, spin Bordism at once. So the prime 2 is hardest, because if you care about 2 torsion, you have to deal with the fact that spin and SO are not the same. But at the double cover at odd primes is irrelevant. And so fermion parity is the reason that, mathematicians often say 2 is the oddest prime. All primes are odd, 2 is the oddest, et cetera, et cetera. And so that's where things get the most interesting. And so that's where I'm going to focus on probably today when I talk about atoms. So the first thing that I'm going to talk about is just SL2. So for SL2, you care about duality, and you're not worrying about fermions. And the tool we're going to use is something called the Meyer-Vietoris sequence. So this is a standard tool in algebraic topology that is typically, people typically use it to compute like homology or cohomology, but you can also use it to compute Bordism. And so I'll show you how that goes. The first thing we need to do, though, is we need to get from algebra, which is the symmetry group, to topology. Meyer-Vietoris takes in topological spaces. And so we need to get from SL2 to something that we can apply Meyer-Vietoris to. So how do we do this? So there's a construction, which for every group, every topological group rather, so maybe, if you like, you can think of it as there's a Lie group, and you produce a topological space, and the cohomology of this topological space is the group cohomology of G. You could also think of this as characteristic classes for G gauge fields. So all of these are cohomology classes, and you can ask, well, where do they come from? And the answer abstractly is to build this space. And that is, so that's how we're going to get from algebra to topology. The other nice fact is, well, we want to study spin Bordism with a G symmetry with no mixing. So we don't care about fermions, or G doesn't act on fermions. This is an object called spin Bordism of the space BG. And spin Bordism is what's called a generalized homology theory. It satisfies all of the axioms of ordinary homology, except for the one that says, oh, we know it, except for the key one that ensures that the value on a point is trivial. And so you get different groups. But the point is, all of the other axioms are satisfied. So there's stuff like Meyer-Vietoris sequences, long exact sequences of a pair. And therefore, we have all the powerful tools that homotopy theorists have been developing. You can sink them into generalized homology theories and learn a lot. And that's how we solve these problems. So as I mentioned, there's this amalgamated product decomposition of SL2. And I mentioned this thing about classifying spaces. Well, so here, this equals is a little bit, I think this is the kind of thing that would make some of my math friends a little bit uneasy. There's different models for BG, and they're all homotopy equivalent, so you get the same answers out. But in my favorite model for BG, the one called the bar construction model, it is literally true that BH1 and BH2 are subsets of BG, and literally BG is the union of them in an amalgamated product decomposition. And their intersection is the thing you're amalgamating over. So, people like to mess around with like homotopy equivalences and whatevers, but here it's literally unions and intersections. Now, this is the setup that you apply the Meyer-Vietoris sequence to, a space covered by two things, and then their intersection is something that you also know. So one consequence is that there's a Meyer-Vietoris sequence for group cohomology. Something which is known is in textbooks on group cohomology, but also for generalized homology and cohomology. And that's what we're going to use. So it takes this form. There's the intersection, there's the two things that we intersected, and there's the union. So K, H1, H2, and G. So this works for any amalgamated product, which is worth mentioning because there's plenty of other interesting amalgamated products out there. So what does this look like for our specific example SL2? It looks like this. We start with the spin Bordism of BZ2, which is known. We map to the spin Bordism of BZ4 and BZ6, also known. And then we get out the thing that we wanted. So what we're going to do next is I'm going to show you how this computation works in a couple low degree examples, so very small n. Before I do that, who's got questions? All right. So here is this thing, this long exact sequence. So what a long exact sequence means is for each map, so maybe I should write it like this. Let's say we have call this omega because it's a Bordism group. So in a long exact sequence, the image of F is the kernel of G. And this simple condition gives you a lot of, gives you pretty tight controls on what the groups are. And so remember, everything over here is known, and everything over here we will determine. So how does this go? So the first thing is, let's fill in the spin Bordism groups of BZ2. This is the simplest. So omega 0 spin Z2, generated by a point, copy of the integers. Omega 1 spin Z2. It's a Z2 plus Z2. Omega 2 spin Z2, it's a Z2 plus Z2. So the generating manifolds are also known. We're not going to worry about that right now. Now we fill in BZ4, and you get almost the same Bordism groups. The only difference is here, where here this was generated by RP1, so the circle with its double cover. This is generated by L41, the circle with its fourfold cover. So spin manifolds of the principal Z4 bundle is what's going on here. So that Z2 enlarges to a Z4. These Z2s are the same. Likewise here, this is an isomorphism. This is an isomorphism. So let's fill in a little more. So what have we got here? Each of these maps is an isomorphism. Each of these maps is an isomorphism. And each of these, the first factor is an isomorphism, and the second one is not an isomorphism. So inclusion from Z2 into Z4 or Z2 into Z6. Now we can use exactness. So right here, this map, the image of F is things of the form X minus X. X comma X. Because we said, oh, this map is just an isomorphism on each factor. So that's the kernel of G. So that implies that the co-kernel is isomorphic to Z. So the image of G has to be isomorphic to Z because there's two Z summands here. And that's the kernel of H by exactness. But kernel of H is everything because H goes to 0. So this thing we have deduced is isomorphic to Z. And the only thing we used is that condition that the image of F is the kernel of G and the image of G is the kernel of H. So you can use a sort of similar, argument with a little more flavor to do the same thing here and to learn that this is Z2 plus Z2. And so the key idea was that both of these maps are isomorphisms, so you can repeat the analysis that we did before. Now, the thing that we were actually interested in was omega 1. Now, the first Z2, you can repeat the same argument, and so you get a copy of Z2. And the second one, well, the second one is a little bit interesting, because, but you can do a sort of a same version of this analysis where you can say, okay, well, what is the image of this map and of this map, Z2 into Z4, Z2 into Z6, and you'll end up getting that you'll get Z4, but then Z3 coming from Z6. And so so you play around with just this relation MF equals Kerr-G over and over and over, and then you learn your Bordism group. So just to clean it up, here's the final answer. Before I move on, who's got questions about any of this? Like what any stuff that is or isn't confusing or wanted to ask? Okay. So we just did the first couple groups. You can do the same story goes all the way up to dimension 11. Maybe you have to work be careful a little bit one prime at a time, but it's really build on the Meyer-Vittori sequence and known computations. So this one was like assembling previous ingredients. But for the metaplectic group, the Meyer-Vittori sequence applies, but these things are a little more interesting. And so some work has to be done to compute the input to the Meyer-Vittori sequence. For GL plus, that's also true. You know, the Meyer-Vittori sequence applies, but one has to compute the input. So now I'm going to tell you about the main course. And so this is where you have fermions, and you have this reflection. And so this is sort of the most general version of the 2B duality group. And we're going to use the atom spectral sequence in order to compute the input to the Meyer-Vittori spectral sequence. Or sorry, Meyer-Vittori long exact sequence.
I have a question about that. So
go for it.
You said that the Meyer-Vittori sequence works when you have when you're just taking, you know, Bordism of a classifying space without the mutual quotient by Z2. Mm-hmm. Is there still a Meyer-Vittori sequence even in that other context? As long
good.
As it appropriately matches on the different pieces?
Yes, good. So okay, so Jake is asking about the fact that these mix with spin. And so what we're technically computing is a form of twisted spin Bordism. And the answer is yes, it works. And so one very concise way to say this is play around with the Thom spectra and you'll get the correct Meyer-Vittori sequence. But just like there's a Meyer-Vittori sequence for twisted ordinary homology and cohomology, there's one for twisted spin Bordism. So, you know, one should be careful, but the same story is true.
The twisted spin Bordism is literally twisted cohomology in the sense of the normal sense of twisted cohomology, like twisted K theory or whatever.
Yes. Yeah.
Great.
Yeah. So, but in this case, it's like the easier twist, where it's just like the twist is described by a vector bundle, as opposed to like something more complicated in the homotopy theory sense. So what that means concretely is that there's sort of a representation of GL2Z such that the spin cover is the is GL plus 2Z. And since it came about as a pin plus cover, that's true. And so you can use that to define the twisting, and it's easier to work with those kinds of twists. I don't know if this is helping at all. I'm sorry.
No, it's definitely helping. Thank you.
Okay. And then, yeah, so the conclusion is you look up in some paper, the twisted Meyer-Vittori spectral sequence exists. So life is good. Were there more questions? Okay, I'll go ahead and go on. So the thing that we want to show is that the inclusion of this dihedral group as rotations and reflections of an octagon induces an isomorphism on Bordism when you only care about two torsion and free summing. So throw out odd torsion. And this is so the odd torsion could be computed by other methods. I'm not going to worry about it. So the idea is D16 is an amalgamated product in a dumb way. We're taking D8, we're amalgamating it with D8. So those cancel out and you just get D16. But you now get a map of amalgamated products into D16, D8, D24, where D8 includes into D24. So this gives you a map of Meyer-Vittori long exact sequences. Now you're really in homotopy theory land. And what do we know about these maps? This map is literally the identity, as is the map on the far right. The D16 map is also the identity, And this one is the identity, or sorry, it's an isomorphism at p equals 2 only. And this ultimately has to do with the fact that the index from D8 into D24 is not divisible by 2. So then you conclude by something called the 5 lemma. So this is some tool in homological algebra. It's really a lemma that this is also an isomorphism at p equals 2. And relevant to Jake's comment is that this is technically twisted. So in this diagram, this is kind of a lie. You need to twist D16 spin Bordism, but this can be done. This can be accounted for. The Meyer-Vittori stuff works. It would have taken a little bit of a digression to make that work. So just with that in mind, the argument is exactly the same. And so now we want to understand the atom spectral sequence to understand the twisted version of this group. So for time reasons, I'm going to try and go through this relatively quickly. The first thing I should probably say is, what is a spectral sequence before we even say atoms? And so a spectral sequence is an approximation scheme. There's something you want to compute and it's hard, but you understand how to do something closely related to it. And it shows up in algebra, geometry, topology, these days in physics sometimes, usually because physics cares about geometry and topology. So you start with something called the E2 page, and it's a table of abelian groups, E2, indexed by two integers, S and T. And the E2 page has differentials. So these are maps on the E2 page that shift the degree as indicated, S plus 2, T minus 3. And they form a chain complex, which is to say D2 squared is 0. Now you take the homology of this thing, and you get another table of abelian groups called E3. E3, for homological algebra reasons, also carries differentials, and the degrees are different. But they form a chain complex. You can take the homology of it again. You get E4. E4 is differentials. You take the homology, you get E5, and so on, and so on, and so on. And you hope that this converges. And in applications, if you're developing spectral sequences, you may have to care about this. But in applications, you look up where someone has proved this in like the 70s, and then you say, voila, it converges, great. And it tells you the thing you wanted to calculate. There's something called an extension problem, which is, it regards to all this stuff, relatively minor. I'm not going to worry about it right now, but it is a thing to keep in mind. That small bridge to get across. But the E infinity page tells you the thing you wanted to calculate. So you start off with the approximation, the differentials make the approximation better and better, and you arrive at the answer.
Hey, Arun, sorry to interrupt.
Go for it.
So to let you know, you have 4 minutes left, including the questions.
Okay, what I'm going to do then is I'm going to skip some of this stuff. So the input is something that is like cohomology, so that's not so hard. So what does the E2 page for atoms actually look like? By the way, thank you for the time reminder. It looks like something like this. The differentials are in these degrees, so most of them vanish. I mean, yellow to orange doesn't, but like this thing, for example, is 0. So most of them are gone. The vertical line calculates omega k. So this is omega 0, this is omega 1, this is omega 2. So omega 0 looks big, omega 1 is small, omega 2 is small. These things will have differentials. And so if you end up concluding, if you look, there's just 2 pieces here. So in omega 1, there's Z2 plus Z2, which correspond to duality bundles given by a reflection in GL2 or a rotation. So the rotation came from spin MP2, so it's supersymmetric, so you get the E7 brane, but the reflection doesn't. And it breaks supersymmetry, and so you end up getting the R7 brane. So we saw omega 1 spin BSL2 gave you Z2 plus Z3 plus Z4 close to the abelianization of SL2, and the GL plus 1 gave it exactly the abelianization, Z2 plus Z2. There were more things. I'm going to skip talking about generators. So what I'm going to talk about is the summary in the future, and then I'm going to be done. So what we did in this paper is, so we applied the cobordism conjecture for the type 2b duality groups. And the test was spin MP2 bordism, which was related to supersymmetry preserving backgrounds. And we used it to then study spin GL plus bordism, and we learned things about non-supersymmetric backgrounds, in particular the R7 brane. In the future, well, there's lots of other duality groups to study, T and U dualities, other things like that. Or we could try and apply the calculations we did to other to quantum field theories, generalized symmetries, et cetera. For example, this is not the only place there's an SL2 in QFT or in physics, and so it'd be useful to take these groups we computed and use them somewhere else. And finally, to tie back to mathematics, my own homeland, is there's this notion of motivic bordism in algebraic geometry, and the fact that F theory typically comes with an algebrogeometric flavor. And it might be interesting to relate this to like the motivic story. and the things that people have already done in both F theory and in mathematics. So sorry for cutting so close to the timing, but I'm all done. So thanks for listening. And please let me know if you've got questions.